Hello, Mr. Dubs. I hope you are ready for today's lecture. Seems like it's going to be only the two of us for now. I hope the others are going to join later.
Yeah, that's all right.
So, are you ready to begin?
Yeah, sure.
All right. Cool. So, welcome to day 6 of month 2. Right. So, for this week, we're just going to be looking at data structures and algorithms. Right. We're not going to dive deep into them. I want you guys to have an understanding of what algorithms are and what they actually do. Right. So for today, I want us to look at big O notation. Right. Big O notation and algorithm thinking. Right. This is what we're going to be looking at for today. Right. So this lesson is slightly different from some of our previous lessons, right? So today we're not mainly learning a new Python syntax, right? We're learning how to think like programmers. Right? As programmers, it is not enough for our code to work. We also need to think about what happens when the amount of data becomes much larger. A program may work perfectly with 10,000 users. A search may feel fast when we have 20 records, right? But what happens when the database contains 2 million records, right? So big O notation gives us a way to describe how the amount of work performed by an algorithm grows as the amount of data grows, right? So big O, it describes how an algorithm, right, how an algorithm grows as the input grows, right? So this is what our big O means, right? So big O notation, it helps us to compare different what approaches, and then so that we can decide the best approach to take. So right, okay. So right, an algorithm is a sequence. So, an algorithm is a sequence of steps, right, used to solve a problem. So an algorithm is just a sequence of steps used to solve a problem, right? So an algorithm does not have to be complicated, right? So if I, for example, if I use a dot sort method in a list, right? This is also an algorithm. There's an algorithm behind this method. So an algorithm doesn't have to be complicated, right? So the question big O helps us answer is this: how does the amount of work change when the amount of data increases, right? So the question big O helps us answer is this. I'll repeat it again. How does the amount of work change when the amount of data increases? Right. So one important thing you guys should know is that big O does not normally tell us the exact seconds. Right. We are not saying this code takes exactly 2 seconds or exactly 5 seconds, right? Different computers have different processors, so they have different processing speeds, right? So the same program may run faster on my laptop, but it may run slower on your laptop, depending on your laptop's processor, right? So big O ignores many of those small differences. Instead, it asks how how the work grows, right? So big O just asks how the work grows, right? So big O equals to growth, right? So big O equals to growth, right? So when it comes to big O, you often see the letter N in big O notation, right? So N, this letter, it stands for the amount of what input data, right? So the N, it stands for wait okay stands for the amount of input data, right? If we have a list of students, N can represent the number of students. If we have 100 students, then N is what? 100, right? So usually you are going to see something like 0 N, right? So you can read this as, let me comment it out. So you can read this as the amount of work grows with the amount of data, right? So any questions before I get into the code?
Can
Yes,
you hear
Mr.
me?
Dubs.
Hello?
Yes, I can hear you.
Okay, yeah. So this big O, it only, it's
Yes, we can look at it that way.
okay. Okay.
So with big O notation, it helps you decide which algorithm are you supposed to use for a certain situation. So that you can always
Okay.
choose the fastest algorithm.
All right.
All right.
Big O is used to describe uh, what you are saying.
Can you repeat that? I'm not getting it.
Okay. How can I put this? Okay, so right, let's take for example the program. I'll give an example of what we've been doing, like the that's called database, right?
Okay.
So let's say that what we were, how we were coding, right? We can describe we can use big O. If okay, let's say maybe the inputs that we did, maybe we use a lot of code for coding that. Is that what we are really getting at here? That the steps that we used. Sometimes we would use a code, a longer code to do something that we could have done easier. So is it the input that you are referring to here, the data?
No,
Still
so
not getting
the input that I'm referring to, it can be, for example, I like the list of how many students, or
okay.
basically just the data type that you're working with, the amount of
Or the
data
data.
or names, etc.
Okay, okay. Also, the more the names, the more we will be saying that our input is growing.
Yes, that's correct.
Okay.
That's why we
Yeah, it's
say,
okay.
yeah, so that's why we say n equals to the amount of input data.
All right. Yeah, it's okay. I'm
Okay,
getting the picture.
I'm getting, oh, okay, then that's great. So I want us to look at what constant time. What constant time, right? So constant time is what? 0, open brackets, 1. This is constant time, right? So, okay, constant time, it means the operation takes roughly the same amount of work regardless of how much data exists, right? The operation takes roughly the same amount, right? The same amount of work regardless of how much data exists, right? This is what constant time stands for. Right. So with Big O notation, there are many times within it, right? So this constant time is one of the most common Big O notation algorithms, right? For example, let's say we have a students list, right? We have John, Mary, and Anna, right? For example, let's say print students 0, right? Right. So this program, right, it's accessing the first item in the list, right? Python does not need to inspect every student, right? It directly accesses what the thing that's it is this specific what index, right? Even if this list has 1 million students or 1,000 students, Python will only access what the student at this particular index, right? So the amount of work does not grow with the size of the list in this example. That is why list indexing is considered what constant time 0, 1. So which means that no matter how much data you are working with, it will always take the same time. Python knows what to fetch and exactly where. So this is our constant time. Right? Even if we add another student, right? Nothing will change. It will still take the same time because Python already knows that I'm only supposed to access what index is 0. Right? So do you all understand how constant time works? Yes, Mr. Dubs.
Sorry, that was a mistake. Sorry.
Okay, that's fine. So does anyone have a question with constant time? So we all understand constant time. Right. So we also have what you call linear time. Right. Linear time. Right. 0 n. Right. So 0 n, this is linear time. Let me comment this out. Okay. Let's say we have a list again. Let's say we have students equals to, let's say, Brandon, John, and Mary. Right. Let's say for student in students. Right. Print student. Right. So here the loop out visits every student using our temporary variable student, right? If there are 3 students like in our list, the loop runs 3 times. If there are 1,000,000 students in the list, then the loop will run what? 1,000,000 times, right? So the amount of work grows directly with the amount of data. This is what you call what? Linear growth, right? So with this data type, with this big O notation, linear time, right? The amount of work so with linear time, the amount of work grows directly with the amount of data. This is called linear growth, right? This is called linear growth. So that's why we use a 0n to describe it. So when you're working with our Pico notation, whenever you see 0n, always know that it is linear time or linear growth, right? So one loop over a collection is often a strong clue that you may have what? 0n complexity, right? So one loop over a collection is often a strong clue that you have what? 0n complexity. So the amount of work grows directly with the amount of data. This is linear time, right? So just because it took 5 seconds in this list doesn't mean that in the next list it's also going to take 5 seconds. It's going to depend on the amount of data that it's going to loop over, right? So any questions with linear time? Any questions? Right. So no questions with linear time. Okay. So let's move on to what? To quadratic time. Right. Quadratic time. Right. Right. So quadratic time is is a complexity that grows what much faster. So it's 0 open bracket n to the power of 2, right? So it's not this big 2, it's what n to the power of 2, right? So this is what a quadratic time, right? So with quadratic time, we have what a loop inside another loop. The outer loop goes through every student, right? For every student in the outer loop, the inner loop also goes through every student, right? Okay, wait, so let me just copy this, right? So here we have what our list with students, right? Right. So here we have a list with students, right? So let's say this is student 1, for student 2 in students, right? Print student 1 student 2, right? So with quadratic time, we have what? We have a loop inside what? Another loop, right? We have a loop inside another loop, right? So here we have what? This is the outer loop. The first loop is the outer loop, right? And then this second loop is the inner loop because it's inside another loop. And the loop that's at the beginning, the parent of the loop, is, we call it what? The outer loop, right? So what? Here we have what are 3 students, right? So with 3 students, that means that we are going to get what? 9 combinations, right? If we have what? 10 students, that means we're going to get what? 100 combinations, for example. That's because since we have 3 students, it's only going to be what? 3 multiplied by 3, right? So it's going to be 3 multiplied by 3, right? If we had let's say 10 students, it's going to be what? 10 multiplied by 10. If there are a million students, then it's going to be what? A million multiplied by a million, right? So then that's how we're going to get how many combinations, how many combinations we have, right? So with so this is what we call what? A quadratic time. So you notice how faster the amount, how much faster the amount of work grows, right? You can easily grow from 9 combinations to 100 combinations, right? That is why nested loops can become expensive when working with large collections. So because the amount of work grows very fast, that means that your program is going to take much more time to run. It's going to take much more time to execute, right? It's not going to run instant, right? So this is what we call what? Quadratic time, right? So remember that with 0 1, it stays constant every time, right? It can take is, you know that with 0 1, it's always going to be 5 seconds, it's always going to be 10 seconds, it will be constant. And with 0 n, it always grows what? Depending on the input, right? And with 0 n squared, it grows much faster because the input is effectively multiplied by itself. Right? If the input is what is 10, it's going to get multiplied by itself, which is 10 again. Right? So big O helps us predict which algorithm will struggle first as our system becomes larger. Right? So I want us to look at algorithm thinking. Okay, before I move on to algorithm thinking, does anyone have a question with quadratic time? Anyone? So no one has a problem with quadratic time. Okay, so let's move over to algorithm thinking, right? So algorithm thinking, right? It means asking whether there is a better way to solve the problem or there isn't, right? Okay, let me see. Algorithm thinking, right? So algorithm thinking just means asking, right? So algorithm thinking just means asking whether there is a better way to solve this problem, right? So you don't only ask, does my code work, right? You also ask questions like, how much work is my code doing? Does it repeat unnecessary work? What happens when the data grows? Can I use a better data structure? That is what you call algorithm thinking. You ask yourself, should I use a list in this situation, or should I use a set, or I should use a tuple, right? And how much is my code doing? Do I need what nested loops or I don't? Does my code repeat unnecessary tasks or it doesn't? Right? Those are some of the questions you're supposed to ask when it comes to algorithm thinking. Right? So as a good programmer, you're always supposed to think about performance, about how much faster your system can run. That is what you're always supposed to think about, how much faster your system can run. Right? Any questions so far? Any questions? Yeah. So we're all good so far. We are all on the same page. Okay, that's fine. So I want us to use this example as searching our example, right? So let's say we need to check whether usernames exist, right? So we have a list called what? Usernames. Let's say we have Brandon, we have Brian, we have John, Tadiwa, Nyasha, right? is join in usernames. So this is a list, right? Python may need to search through the list, right? For a list, membership checking is generally what 0n, this 0n, right? Because it grows directly with the amount of data. Today we can have 10 users, and then tomorrow we wake up to 20 users. 1 month later we wake up to 1,000 users. So generally membership checking is what 0n, right? Right. Okay, so okay, here we use the list. I want us to try a set. So a set uses what so sets use a structure, right, designed for very fast membership checking compared to what, to a list. Right. So on average, right, checking whether what an item exists in a set is usually what 0 1, right, compared to what, to a list, right? So on average, checking whether an item exists in a set is what 0 1. So for this kind of task, checking whether a username already exists using a set is much more faster and much more efficient than using any other data type, right? Because on average, a set returns what 0 1, which is one of the fastest time complexities, right? So sometimes performance improves not because we write a clever loop, but because we chose a better data structure. So choosing a better data structure for a certain task, it makes a lot of difference, right? Here, if I use a set, then that means we're going to use what, linear time. But if I use a list, it means that we're going to use what, linear time. But if I change from a list to what, to a set, that means that we moved from linear time to what, to constant time, which is faster than linear time, right? So choosing the right data structure, right, is part of algorithm thinking. It's part of algorithm thinking. So that is why before you start coding, you need to know what you're supposed to do. You need to know the type of data structures that you're supposed to use for a certain task, right? So always remember that choosing the right data structure is part of algorithm thinking, right? So any questions are with big O notation and algorithm thinking? Any questions? Okay. So we all understood what algorithm thinking is and what big O notation is. Okay, if that's the case, then so today I wanted us to only look at what at big O notation and algorithm thinking. So tomorrow we are going to work on our first algorithm, which is going to be the searching algorithm. Right. So if we don't have any questions, then this is the end of today's lecture, and I hope you guys can revise big O notation and algorithm thinking before we begin writing algorithms.